curious, slightly hushed tone. You type a prompt, hit enter, and seconds later, an artificial intelligence writes complex code, discovers a chemical compound, or renders a hyper-realistic video. It feels frictionless. We often imagine these algorithms floating in a clean, weightless space we call the cloud. Authoritative. But the cloud is a physical place. It is a sprawling network of massive buildings packed with servers, miles of fiber optic cables, and specialized chips that devour electricity. The sheer size of modern AI infrastructure is difficult to comprehend. A single data center can easily be large enough to park a Boeing 747 inside. Because technology companies are locked in a competitive race for computing power, waiting years to construct these massive facilities outdoors is too slow. To keep up with demand, they are now manufacturing data centers inside enormous factories. Before an AI model can answer a single question, an entire industrial ecosystem of steel, cooling, and power must first be built to support it. This diagram shows the floor plan of a modern AI data center factory. Instead of a chaotic construction site, this space operates as a precision manufacturing plant, divided into 4 distinct manufacturing zones. The process starts in the structural zone. Massive coils of raw steel arrive on heavy rail lines. Automated machines slice the metal, while robotic arms weld joints, forming the physical skeleton of the data center. This animation illustrates the factory's core innovation, prefabricated modules. Instead of building on a dirt lot, manufacturers assemble entire data center sections into giant industrial blocks that snap together. Constructing these indoors enables instant strict quality checks, avoiding weather delays and shaving months off standard timelines. From the structural area, the modules move into the power hall. A single large AI facility consumes staggering amounts of electricity, often requiring as much power as a small city to operate. To manage that massive load, technicians assemble uninterruptible power supply, or UPS systems. These units rely on massive battery arrays, some larger than a supermarket, to provide instant backup electricity while diesel generators spin up. If a facility loses power for even a fraction of a second, the sudden crash could permanently damage billions of dollars worth of computing equipment. The UPS system acts as a massive shock absorber to ensure that never happens. Supplying power is only half the engineering challenge. The real enemy of tightly packed AI hardware is the extraordinary amount of heat generated by the processors. In older data centers, enormous fans simply pushed cold air through the server racks, but modern AI chips run so hot that traditional air cooling is completely obsolete. This server rack cross-section shows the modern solution: liquid cooling. Technicians route carefully bent copper pipes to circulate coolant directly to the hottest components. The spacecraft-like tolerances mean every laser-welded joint faces intense pressure tests, ensuring years of continuous operation without springing a leak. A single drop of coolant inside a high-density AI rack could destroy millions of dollars of hardware. Mastering this precise thermal dynamic is the only thing preventing a catastrophic cluster meltdown. Once the cooling loops are sealed, the computing power takes shape in the integration zone. Technicians carefully load empty racks with GPU servers, connecting them with thousands of fiber optic cables in a highly choreographed sequence. This wireframe diagram shows a digital twin, a virtual copy of the server rack. Engineers use it to verify every cable route in real time. If a connection hits the wrong port, the system instantly flags it, ensuring engineers don't spend days tracing one misconnected fiber. Next, completed racks roll into the burn-in chamber. It is a deafening environment, where massive industrial fans spin at maximum speed under intense hardware stress. Engineers load the racks with synthetic AI workloads, forcing the machines to operate at full capacity. The logic is simple: push the components to their absolute limit, so that any defective parts fail right here in the factory, rather than out in the field. What is fascinating about this floor is the feedback loop. The machine vision cameras inspecting the welds and the algorithms tracking the logistics are powered by artificial intelligence. AI is actively helping manufacture the very infrastructure it needs to grow. By the end of this assembly line, a completed cluster sitting among the forklifts temporarily holds enough raw computing power to train an entirely new frontier AI model. The final step is getting this massive equipment out the door. These fully integrated, multi-time modules must be transported out of the factory to data center sites that may be hundreds of miles away. Transportation teams map routes down to the inch to clear bridges and power lines. Specialized heavy haul trucks move the module